Have you ever hit send on a message and just wondered, how does it actually get from your phone to someone else's, like halfway across the world in less than a second? Well, today we're going to trace the incredible, invisible journey of just one single message from start to finish.
I mean, really think about it for a second. You type hello, and boom, a screen lights up on another continent. It honestly feels like magic. But it's not magic. It's this amazing feat of engineering that follows a very specific and very challenging path. And it turns out pretty much every piece of digital communication, we're talking emails, video calls, you name it, follows this same basic chain. You've got the source, where the message is born, the transmitter, which sends it on its way, the channel, which is the path it travels, and finally, the receiver, which catches it at the other end. This is our roadmap. Okay, so first things first, we have to take an idea, our hello, and turn it into something physical, right? You can't just send a thought through a wire. It has to be translated into a language that electronics can understand. And that translation is what we call a signal. To travel through the digital world, our message becomes this changing electrical voltage. Think of it like a little electrical mimic, perfectly copying the pattern of your voice or the data in your text. So what actually does this magic trick? It's a little device called a transducer. A microphone is a perfect example. It literally hears the energy from the sound waves of your voice and converts it, on the spot, into an electrical signal. And with that, our message is ready for the next step. But there's a problem. Our brand new electrical signal is, well, it's kind of weak. It's what's called a low-frequency signal, and on its own, it's not going anywhere far. To really travel, it needs a serious upgrade. It needs a vehicle. And this is the real puzzle, isn't it? If we tried to transmit these low-frequency voice signals directly, we'd need antennas that are miles long, literally. So how do we make that work with the tiny little antenna tucked away inside your phone? The answer is this absolutely brilliant process called modulation. The best way to think about it is like this. Our weak little signal is a passenger, and modulation puts that passenger onto a super fast, high-frequency jet plane called a carrier wave. This jet has the power to cross huge distances with no problem. And this right here really shows you why it's a game changer. Without modulation, you're stuck with signals that can't go far and need ridiculously huge antennas. But with modulation, suddenly we can use small, practical antennas that fit in our pockets, paving the way for, well, our entire modern connected world. So when you boil it all down, modulation is doing two absolutely crucial things. One, it lets us use tiny antennas, and two, it's what allows thousands of different signals, all the different radio stations, all the cell phone calls in a city, to fly through the same airspace at the same time without crashing into each other.
All right. Our message is riding high on its carrier wave. It's just been launched from the transmitter, and now it has to face the most dangerous, most treacherous part of the whole journey. It has to survive the channel.
As our signal blasts off from the transmitter, it's perfect. Just imagine this clean, beautiful, pristine waveform. It's an exact electronic copy of our message, all set for its trip. But here's the thing. The signal that arrives at the destination is never the same one that left. It's been battered, corrupted, and distorted. You can still see the original shape in there somewhere, but it took a serious beating along the way. And this is the fundamental problem of all communications. So what is this channel? It's just the physical thing our signal travels through. It could be the air for your Wi-Fi, the copper in an old phone line, or the glass in a fiber optic cable. The key thing to remember is that none of these channels are perfect, silent tunnels. In fact, the channel is actively trying to mess up our signal in 3 main ways. It adds noise. Think of it like random static. It causes distortion, which actually bends the signal out of shape. And it creates interference, which is when other signals bleed into ours and cause confusion. And out of all those threats, if you ask any communications engineer, they'll tell you straight up, noise. Noise is the biggest enemy. It's the constant, random hiss of the universe that our tiny signal has to be powerful enough to shout over. So, after somehow making it through that gauntlet, our wearied, battered signal finally arrives at the receiver. Now comes the really delicate part, rescuing our original message from all that damage and noise. I like to think of the receiver as being part doctor and part translator. First, the doctor has to step in and heal the damaged signal, clean up the noise, fix the distortion. Then, the translator has to turn that clean electrical signal back into something we can actually understand.
And this happens in 3 main steps. First, a filter acts like a bouncer at a club, zeroing in on our specific signal and kicking out all the unwanted noise around it. Second, it demodulates. That's where it lands that supersonic jet and lets our passenger message hop off. And finally, another transducer steps in to translate that electrical signal back into sound or text or video. Our hello is back. Because at the end of the day, this whole incredibly complex system has just one goal: faithful transmission. A communication only counts as a success if the message that arrives is a true, accurate, faithful copy of the one that was sent. That's the whole point.
So that's the wild, microscopic journey of one little message. But let's zoom out for a second, because understanding this journey is a really big deal. Get this. That incredible journey doesn't just happen once in a while. It happens more than 300 billion times a day, every single day. Each one of those is a tiny little miracle of engineering, successfully fighting off noise and distance. So this invisible process, this journey from thought to signal, surviving that noisy channel, and being faithfully put back together, that's not just a cool piece of science. It is the fundamental engine that powers our entire connected world. It's the science behind our global conversation. And that kind of leaves us with a pretty big question to think about. As our world keeps getting more crowded with signals, more devices, more data, that channel is only getting louder and noisier. So the real challenge for the future is, how are we going to invent new ways to make sure our most important messages can still complete their incredible journey?